Skyscrapers are more than just concrete and glass stretching toward the clouds. Behind their sleek facades are engineering choices that defy logic and push the limits of human innovation. From hidden levels to structural designs that seem impossible at first glance, these towers prove that our greatest architectural achievements are also our strangest. Their secrets reveal just how extraordinary these monumental structures really are. Number 5. Skyscrapers create their own micro-ecosystems. Skyscrapers are often tall enough to form entirely distinct micro-environments that differ significantly from conditions at ground level. Higher altitudes can be several degrees warmer due to rising heat from traffic, infrastructure, and reflective materials below. This warmth gives rooftop gardens, trees, and even specially curated greenery the ability to thrive where street-level soil and shade might not allow it. Some buildings host beehives on their upper platforms, where bees pollinate rooftop flora without competition from ground-level disturbances. Birds also adapt by nesting on ledges hundreds of feet above the city, taking advantage of safer perches away from foot traffic and predators. In major urban centers, skyscrapers have even incorporated hydroponic farms in unused maintenance spaces to grow vegetables, herbs, and small produce for residents and restaurants. These ecosystems, shaped by altitude and warmth, demonstrate how skyscrapers become uniquely self-contained environments that support life in unexpected ways. Beyond gardens and wildlife, these micro-ecosystems also form subtle climate patterns around the buildings themselves. Heat rising up the exterior walls can create small air currents that pull moisture higher and change how condensation settles on windows and open surfaces. Wind sweeping through narrow gaps between towers can accelerate as it channels upward, allowing certain hardy plants to adapt to stronger gusts. In cities like Chicago and Dubai, rooftop soil beds at several hundred feet have been carefully designed to resist drying winds, while irrigation systems use collected rainwater to sustain them. Some skyscrapers have experimented with aquaculture on upper service decks, using insulated tanks to raise fish where temperatures remain stable year-round. Wildlife cameras placed on high ledges and spires have discovered entire communities of falcons and urban hawks nesting inconspicuously above the city noise. When viewed from a distance, these towers seem like sterile monoliths, but up close, they reveal quietly thriving biological zones that wouldn't exist without their height. Number 4. They use counterintuitive materials to stay light. Contrary to what most people imagine, the tallest towers rely on reduced mass rather than raw bulk to remain structurally sound. By using ultra-high-strength steel instead of piling on excess concrete, architects keep a building far lighter than its massive size suggests. These steel frameworks concentrate load along narrow support columns that stretch from the foundations to the top, leaving internal cores hollow to reduce unnecessary weight. Fewer solid interior walls also mean that shafts for utilities, elevators, and emergency systems can run vertically without adding excessive structural load. A lighter skyscraper places less strain on the foundation, allowing builders to dig shallower footings that reach only the more stable layers of bedrock. This also lowers the possibility of gradual sinking or settling, especially in cities built on softer soil. With weight distributed more efficiently, skyscrapers actually grow stronger by becoming slimmer rather than bulkier. This approach gives skyscrapers unexpected flexibility, letting them safely stretch hundreds or even thousands of feet into the sky while minimizing the bending forces acting at their cores. Steel's natural elasticity allows the structure to absorb energy during high winds, small tremors, or temperature changes without cracking. Specialized concrete may still be used, but only in critical areas like central pillars or load-bearing floors where brute compression strength is necessary. To make these materials perform even better, engineers reinforce them with tensioned cables that run inside the frame, creating resilient support that responds almost like muscles. Innovative techniques such as perimeter tube systems have evolved to keep the outer shell stiff and upright, while leaving most interior space conveyor-free and open. In the end, what looks towering and heavy is actually a carefully balanced skeleton optimized for vertical height, aerodynamic stability, and reduced foundation stress. Number 3. The world's tallest skyscrapers hide secret floors. Many of the tallest buildings disguise mechanical floors that don't appear on official listings, resulting in visible height that can't be fully accounted for by elevator stops. These hidden levels hold ventilation systems, water storage tanks, power distribution panels, and the massive machinery that runs dozens of elevator shafts. Often positioned at intervals throughout the height of the tower, these floors ensure that electrical and pumping systems don't lose power or pressure over extreme vertical distances. They also serve as structural reinforcements, tying multiple support columns together to keep the tower rigid. High-security devices installed inside these levels control fire suppression systems and backup generators that can keep a skyscraper operating indefinitely during outages. Visitors rarely see these spaces because they're accessible only to authorized technicians, security staff, and maintenance engineers. Without them, a mega-tall building simply couldn't function at its record-breaking height. The secrecy surrounding these floors isn't just practical, it also affects skyline measurements and real estate bragging rights. Because some of these mechanical spaces aren't counted as usable occupancy, they may artificially increase a tower's height without technically being considered part of its operational floor count. This ultimately influences the rankings of tallest buildings, where inches matter in architectural competition. To maximize appearance, some towers intentionally stack multiple mechanical layers near the top, boosting the spire and pushing their silhouette past rivals. These floors also act as vibration buffers, absorbing subtle shifts that travel through the frame and preventing resonance from forming at upper levels. Although hidden from public view, they are essential to the safety, function, and prestige of the world's highest towers. Every time a skyline race breaks another record, there are always mechanical floors quietly contributing behind the scenes. Number 2. Skyscrapers can change local weather. Super tall buildings reshape airflow patterns and temperature gradients around them, creating microclimates that differ dramatically from open landscapes. When wind moves between towers, it accelerates, especially within narrow streets where pressure builds and funnels air into concentrated streams. These fast-moving pockets can flip umbrellas, knock people off balance, and even force cities to redesign plazas with angled walls to redirect gusts. Because the upper third of a skyscraper traps and reflects heat, thermal layers form that alter humidity and condensation cycles. At hundreds of feet in the air, rising warmth from engines, furnaces, and asphalt creates pockets that can slightly influence cloud moisture. Heavy clusters of tall towers have been known to increase rainfall unevenly by pushing air currents upward, triggering localized precipitation. Even the swirl of gases around their peaks can alter smog distribution and change how haze settles against the skyline. This weather-shaping effect isn't isolated to roof height. It ripples across entire districts. In some cities, sidewalk wind patterns adjusted building by building to reduce unpredictable gusts, while other districts built wind baffles to break up air pressure near entrances. Thermal zones around skyscrapers can also raise nighttime temperatures by several degrees, storing daytime heat and radiating it back after sunset. A group of towers can even create a chimney-like effect, pulling warm air upward and shifting cooler air back down toward the street. Over decades, these patterns can change plant survivability, humidity balance, and seasonal storm paths in localized pockets. Though subtle, the interactions between mass, heat, and wind prove that skyscrapers are more than passive observers of nature. They influence the environment in ways that urban designers must always account for. The look of a skyline is only the beginning. Its invisible climate footprint reaches far beyond its outline. Number 1. Some skyscrapers are designed to sway several feet. Many modern skyscrapers are engineered to move along their upper floors, flexing slightly when wind currents push against them. At several hundred feet above city streets, wind pressure amplifies dramatically, making rigid structures dangerous because fixed resistance could cause cracks or stress fractures. To counter this, builders use structural elasticity that allows the top floors to sway by up to several feet in strong weather systems. The sway is slow, smooth, and intentional, designed so that occupants rarely feel it as anything more than a gentle shift. Much of this is controlled by massive weights known as tuned mass dampers, sometimes weighing hundreds of tons, placed near the highest interiors. These pendulum-like counterweights shift opposite the building's motion, absorbing energy and reducing wobble that would otherwise make people dizzy. Instead of resisting nature, skyscrapers lean into motion as a form of stability, proving that flexibility can be stronger than brute force. Even the shape of a skyscraper is engineered to help manage this movement, with rounded edges, tapered crowns, and aerodynamic cutouts designed to soften wind flow. Exterior facades may include openings that allow air to pass completely through the structure, reducing drag and lowering the force that triggers sway. Reinforced steel frameworks and cross-braced cores unite the building's spine so that any motion distributes evenly, rather than focusing stress in one area. On especially tall towers, motion sensors constantly track wind and structural flex, adjusting dampers in real time. When gusts strengthen, the building can subtly shift, releasing energy instead of absorbing it. This is why megatowers continue to grow taller each decade. Engineers have learned that controlled movement, rather than rigid resistance, is the true secret to surviving the violent forces found at high altitudes. The next time you look up at a skyline giant, remember that it's quietly bending with the wind, not fighting it. Thank you for watching. If you enjoyed it, please like and subscribe. Until next time.